Professor Hans. She is Professor of Radiation Oncology and Chief Medical Physics in Samsung Medical Center. And I will invite because it is already we are late. So I will invite Professor Han to start his topic on proton beam therapy. Professor Han, please.
Thank you for introduction, Dr. Shukla. It is an honor to be a speaker in the AFOMP webinar. Today, I'll be talking about the proton therapy. After a short introduction, I will start explaining why proton therapy has attracted a large attention in modern radiation therapy. I will then review current and emerging proton therapy technologies, and finally present a short outlook for future technologies. Radiation therapy has been an important modality for cancer treatment. Cancer is a serious disease, second highest cause of death worldwide. Asia has the largest percentage in the global cancer mortality statistics. Cancer is a disease that develops in most organs in humans. The radiation therapy has increased the cure rate above 50% for many cancers. One of the key components for success of the radiation therapy is the ability to focus the radiation to the tumor while minimizing the radiation to the nearby critical organs. Therefore, the radiation therapy technique has been evolved from a two-dimensional treatment to a three-dimensional conformal treatment and intensity modulated radiation therapy. In recent years, the proton therapy has been established as a state-of-the-art radiation therapy. A proton has a unique characteristic of delivering the energy at the end of the track, referred to as Bragg peak. Using this characteristic of the Bragg peak, energy can be strongly focused on the tumor while reducing the radiation dose to normal tissues. The benefits of the proton therapy observed in our institutes are as follows. Patients with an underlying idiopathic pulmonary fibrosis treated with proton therapy exhibit a significantly increased survival outcome compared to the those treated with X-rays. Proton therapy reduced the risk of severe radiation-induced lymphocythemia during chemoradiation therapy for locally advanced non-small cell lung cancer. For hepatocellular cancer patients, proton therapy can limit the dose to normal level. The overall survival rate was higher than that of X-ray therapy. The proton therapy reduced the risk of toxicity associated with chemoradiation therapy toxicity in esophagus cancer treatment. In head and neck cancer treatment, grade 2 mucositis was significantly less frequent in the proton therapy combination group. Superior intellectual outcome was reported in proton CSI treatment of pediatric brain tumors. Hence, acknowledging the benefits, national insurance in Korea have started to reimburse the proton therapy from September 2015 for most cancer disease sites as shown in this list. Likewise, many countries reimburse the proton therapy for specific cancer types. During the last 3 decades, the number of proton therapy centers has been increasing worldwide. As of 2022, 125 centers are in operation, and about 280,000 patients have been cumulatively been treated using proton beams. Recently, a large number of particle centers have been proposed. The number of effective particle centers will be 191 by 2025. A particularly large number of institutes in the Asia-Oceania region have proposed proton over carbon ion centers. Therefore, 79 institutes are expected to be in operation in 2025. Now let me summarize the history of proton therapy technique development. The use of high-energy protons for medical treatment was proposed for the first time in 1946 by Robert Wilson, who was a particle physicist at Harvard University. The first proton therapy to human was through pituitary irradiation to control a metastatic breast cancer at Berkeley Radiation Laboratory in 1954, using a proton beam accelerated by a research cyclotron. Later, an approach to deflect the proton beam using magnet rather than a scatterer for treatment was suggested for the first time by Larsen. He reported a continuous scanning with 187 MeV protons at Uppsala, Sweden. However, the clinically applied technique was spot scanning, which delivers proton beam spot by spot in a discrete manner, developed at NIRS Japan in 1980. In 1988, proton therapy has gained approval for clinical application from the USDA. The first hospital-based proton treatment center was opened in California, USA, 1991. This slide shows a picture from the historic paper that reported the first proton therapy treatment in 1954 using a proton beam accelerated by a research cyclotron. The autoradiographs of the 340 MeV proton beam was taken and was superimposed to orthogonal X-rays image to verify the patient alignment to the proton beams. Regarding the first spot scanning system in NIRS, a system in which each spot was digitally controlled by a microcomputer was developed using 70 MeV protons. This technique was referred to as a spot scanning system. However, each individual subfield was of a centimeter scale, as shown in the figure. Later, the clinically applicable PBS technique was developed in Paul Schroeder Institute and started to be used for routine patient treatment. Using small pencil beams with a width of 7 mm, it was possible to construct an arbitrarily shaped three-dimensional dose distribution. Now let me review the modern proton therapy system and the beam delivery technologies. Proton therapy system is composed of an accelerator, which accelerates protons, beam transport system, which transport accelerators protons to a treatment nozzle, and a gantry system, including a beam delivering nozzle within it. In addition, a patient positioning system, such as a patient couch, position verification system, and radiation therapy planning system are also key components necessary for accurate patient treatment. Among the various components of the proton therapy systems, I will talk about the accelerators, gantries, and the beam delivering technologies. The proton accelerator is the core component of proton therapy. The medically used cyclotron accelerator was conceived by Ernest Lawrence in 1929 and built at Berkeley Laboratory. This initial invention was not for medical use but for research on particle and nuclear physics. Since then, many cyclotrons was built to establish the proton therapy program across the United States at Harvard University, University of California, Davis, and Los Alamos National Laboratory. The research at these facilities, coupled with the technological advances in photon radiation therapy and its delivered method, has advanced the proton therapy to its current position in the field of cancer treatment. Nowadays, several types of accelerators are utilized for proton therapy. This list is a summary of accelerator types. Isochronous cyclotron is the most commonly used accelerator. Some vendors provide a superconducting cyclotron with reduced size and weight. Research on high gradient Linac using a dielectric wall and the laser has been carried out. However, the technologies are not yet sufficiently advanced to be commercialized for medical use. A cyclotron was used as an accelerator for the first proton therapy. After the first use of the accelerator, the medical cyclotron has been smaller and lighter over the last 76 years. As shown in this slide, the superconducting AFOMP cyclotron developed by Mavion Medical System largely reduced the size and weight of the cyclotron. This was the trend of medically used synchrotrons. Using the superconducting magnets technology, the size and the weight of the synchrotron have been reduced. The footprint of the superconducting accelerator is only 50% of the conventional one. Regarding the specification of accelerators desirable for clinical use, I have briefly summarized the specification of a medical accelerator on this slide. In addition to the basic characteristic of the accelerators, the control system of the proton therapy system should have a very good flexibility to be integrated into a third-party radiation verified system. Now let me review the gantry system. The gantry system provides 360 degrees of freedom in beam irradiation. However, the conventional design is huge and heavy. The radius is over 5 meters with a weight over 160 tons. However, the isocenter displacement during the gantry rotation need to be very small, such as smaller than 2 millimeters for full rotation. Similar to the trend of accelerators, smaller and lighter gantries has been developed to reduce the facility footprint, building cost, and the technology cost. This is an example of a half gantry provided by Proton. In conjunction with the robotic arm type couch, which has 60 degrees of freedom of motion, the beam angle can be theoretically directed to 360 degrees. However, the smaller gantry space, such as the Hitachi system, may limit non-coplanar beam irradiation, and the large angle rotation of the couch can increase the treatment time of a patient. This is another example of a small gantry. By changing the arrangement of the magnet path, the total volume of the gantry was reduced to approximately 50% of the conventional type of the gantry. Superconducting technology has been employed in gantry magnet design. This picture is an example of a 360-degree rotating gantry utilizing superconducting magnets. By replacing one magnet, particularly dipole magnet in beamline, with a superconducting magnet, the weight and the footprint of the gantry can be significantly reduced. The radius was reduced to 3.5 meters, while the weight to 40 tons. However, a major challenge emerges owing to the considerably lower ramping rate of a superconducting magnet, which increased the switch time of energy layer during the formation of the SOBP. A very recent characteristic development is a gantry that does not have a rotating mechanism. Bidon Medical developed an ultra-compact proton therapy system using a patented magnet design. The accelerated protons are bent to an arbitrary angle in the superconducting bending magnet and irradiated to the isocenter. However, the design provides a very limited beam angle. Therefore, 0-degree beam and 180 beam are not supported. However, this new concept largely reduced the volume and the weight of the gantry, which is designed the proton therapy system can be introduced in existing hospital without constructing a new building. Now, let me present beam delivery techniques. The techniques used for proton delivery to patient can be categorized into broad beam proton therapy and the pencil beam scanning proton therapy. Both techniques utilize a more energetic proton beam extracted from an accelerator, typically with a beam cross-sectional diameter of 3 or 4 mm. The broad beam techniques broadens the monoenergetic proton beam laterally, allowing the beam to pass scatters over a high atomic number material, and thus the protons are scattered sufficiently widely to cover the target in a plane orthogonal to the beam path. With a double scattering system, the first scattered proton beam passed the second scatterer, making a large uniform field. The broadened beam is shaped using a patient aperture to fit the radiation field to the maximum size on the orthogonal plane to the beam path. Along the depth direction, a range modulator wheel or a Ricci filter is used to increase the small width of the Bragg peak sufficiently to cover the tumor in the depth direction. To ensure that the dose conform to the distal part of the three-dimensional volume of the tumor, a patient compensator is used to appropriately compensate for the variation in the distal depth of the tumor. However, as shown in the figure, a compensator device is unable to match the dose to proximal part of the target volume. This is one of the main disadvantages of the broad beam technique compared to the pencil beam scanning. Another broad beam technique is based on a wobbling system, which was invented to reduce the secondary radiation from scatterer at Berkeley Radiation Laboratory. The wobbling system uses a pair of magnets together with a single scatterer instead of a second scatterer to provide a uniform, large proton beam as shown in the figure. The accelerated proton beam from the accelerator is rotated along a circular path controlled by magnetic field strength and then passes through a single scatterer. This method also produces the fixed size circular radiation field. Therefore, our patient block is necessary to shape the radiation field to fit the maximum tumor cross-sectional area in the orthogonal plane. To create a SOBP in the tumor region, several Bragg peaks of different range with certain intensity should be combined each other. Range modulator field, which is a device providing a SOBP, is basically a rotating field with a step of variable thickness. The instant proton beam sequentially penetrates the observer of a variable thickness of a range. Thus, each thickness of the observer contributes with an individual pristine Bragg peak to composite a SOBP. This figure shows a series of weighted pristine Bragg peaks as well as the resulting SOBP when these are superimposed. A Ricci filter is a plate composed of a lucite or some low-sheet material in which almost triangular Ricci are milled so that proton traveling this plate will pass different material thickness. A bar Ricci filter is a stationary device. This is an effective device for the pulsed beam provided by the synchrotron, since it eliminates the concern about the time structure of the beam intensity. A typical beam Ricci filter is shown in the figure. The bar Ricci filter consists of 30 to 50 bars Depending on the nozzle type, each bar has the same ridge shape. Aluminum is a typical material because it is a loose material fabricating the scattering reduction. Regarding the scanning technique, various modes of particle scanning has been devised for proton therapy. The first is a discrete spot scanning. This is a step-and-shoot approach in which the predetermined dose is delivered to a given spot at a static position. The beam is then switched off. The second is a continuous scanning, which delivers proton continuously without turning off the beam along a line or a contoured path. With the scanning technique, the intensity modulated proton therapy is the most advanced delivery technique, which delivers intentionally non-uniform dose distribution from each treatment field at a given direction. The desired uniform dose in the target volume is obtained after superimposing the dose distribution from all fields. However, in clinical practice, a single field optimization (SFO) technique, which delivers a uniform dose from each beam port, is preferred. This technique reduces the risk associated with the setup and any dosimetry uncertainties. Therefore, the SFO technique is tried first in beam optimization. Only when the SFO optimization does not meet the prescription, the multi-field optimization technique is utilized. The pencil beam technique provides a better dose conformity than that of the broad beam technique. In addition, the following advantages are provided. The scanning method do not need patient-specific hardware, which could be a considerable operational advantage. It is more efficient in beam and energy utilization because almost all protons extracted from the accelerator are used without loss through the scatterer or compensator. It is advantageous in reducing the gantry size. It provides a large field size, which removes the field patching for treatment of a large tumor. However, the scanning technique is very sensitive to the accelerator time structure as well as the organ motion of the target due to the dynamic delivery of the beam. Therefore, possibly the most challenging issue in using the pencil beam scanning technique is the motion mitigating strategy to reduce the unwanted deviation of the dose distribution in the target and the normal tissues. The left show an example of disturbance of the lateral dose fall-off, in which the lateral penumbra of the beam is extended owing to the target motion. The right figure shows an unwanted dose inhomogeneity caused by the overlapping of the two Gaussian-shaped pencil beams. This simulation exhibits the interplay effects of the moving target at scanning delivery of a different extraction rate from a synchrotron. As shown in the dose volume histogram of a target, the interplay of the spot delivery and the tumor motion affect the dose distribution negatively, which results in a lower dose to the tumor and a higher dose to the normal lung. The extent of the dose difference was correlated to the magnitude of the target motion. Thus, it is of interest to propose an approach to minimize the motion-induced uncertainty. One of the methods is rescanning. By repainting the dose several times in the tumor volume, a statistically averaged dose can be obtained. However, this technique does not completely remove the motion effect, and thus adequate margins need to be added to the boundary of the target. Another technique is based on irradiation of the beam only during defined motion status. In clinical practice, a finite gating window is always used. Therefore, the dose deviation due to the residual motion of the target exists even in the gated treatment. The third strategy is a combination of gating and rescanning to avoid dose inhomogeneity by a relatively large number of rescanning cycles within an acceptable irradiation time. The fourth strategy is to reduce the spot distance and thereby increase the overlap of the spots. This overlap strategy can be applied to the depth direction too. The narrow energy spacing in forming SOVP is more robust for dose inhomogeneity induced by target motion. Simulation data demonstrate that a smaller gating window reduced the dose inhomogeneity in the target. However, in increased spot size and the smaller spot distance can increase the gating window while maintaining the homogeneity and thereby enhance the treatment efficiency. Another technique of spot scanning treatment while verifying the tumor position in real time was developed by Hitachi in collaboration with Hokkaido University. Left figure shows a photograph of the nodule with two X-ray images. Tumor tracking works by injecting a gold marker into the patient close to the tumor and obtaining X-ray images from two different directions at a rate of 30 frames per second. The beam is then only output when the location of the marker is within a predetermined range to enable precise irradiation of moving organs. Let me summarize the motion management strategies. Gating or breathing holding process scanning can be a promising solution. Pencil scanning treatment with verifying a tumor position in real time using X-ray images is in clinical use. Increasing overlap can reduce the interplay effect in pencil beam scanning laterally and longitudinally. All developed techniques reduce the deterioration of dose distribution, but not fully eliminate the effect caused by the organ motion. Therefore, reducing organ motion has fundamental importance. Let me review the image-guided radiation therapy technique used for proton therapy. Conventional two-dimensional orthogonal X-ray images have been used to verify the target position at each treatment session. However, in recent years, Combin-CT integrated in gantry system has been developed and used in clinic. Currently, most proton therapy vendors provide Combin-CTs. For carbon ion beam therapy system and some proton therapy system, Combin-CT has also been developed in a unique way to be used without a rotating gantry system. The photo on the left side shows Combin-CT in Heidelberg ion beam therapy centers, whereas the photo on the right side shows the ring-type X-ray imaging system that can scan Combin-CTs in conjunction with the robotic couch. One of the problems of employing gantry-mounted Combin-CT image for proton therapy is image quality. Owing to the large source-to-detector distance, scattered photon contribution is significant. Thus, images are poor compared to those acquired to Combin-CT integrated into X-ray linear accelerators. Many studies using machine learning algorithms are being conducted and an improvement in image quality is anticipated. Now, I'd like to move on and describe the proton dose calculation algorithm. Accurate dose calculations are fundamental for determining treatment strategies. As such, accurate algorithms are inevitably an important factor in reliable treatment, given that tumor control probability and the normal tissue complication probability are step functions of the observed dose in certain disease locations. For clinical use, Two different types of dose calculation algorithms are available, analytical and Monte Carlo algorithms. Until a couple of years ago, the treatment planning system, TPS, had provided only the pencil beam algorithm, which is an analytical algorithm for proton therapy. However, an MC algorithm, which is more accurate in predicting the dose calculation in inhomogeneous media, now supports the pencil beam scanning treatment and is available in commercial treatment systems. The PBA has several limitations, some of which are listed next. It does not accurately consider multiple elastic Coulomb scattering or elastic and inelastic nuclear interactions. It failed to provide an accurate dose calculation in the case of a highly heterogeneous media, such as the lung. The PBA models patient as a stack of semi-infinite layers, thus material encountered by the central axis of pencil beams are considered laterally homogeneous slabs along the depths. Recent studies have demonstrated that the pencil beam algorithm inaccurately calculates the dose distribution for proton beams that are oblique to the patient surface. In particular, when using a range shifter with a large air gap, the inaccuracy is clinically unacceptable even in homogeneous media. The PBA does not provide sufficient accuracy for breast patient treatment, especially with a large air gap between the range shifter and the patient surface. The Monte Carlo algorithm results in a much higher accuracy in all beam configuration tested and is recommended for planning breast patient treatment using proton pencil beam. This is another example of a pencil beam algorithm applied in this case at the interface of a material with different density. Two subspots were incident at the water-bone interface such that only a partial subspot passed through the bone intersect. Subspot A was positioned such that its central axis lay in the water, while subspot B was slightly displaced laterally to have the central axis passing through the bone material. Pencil beam algorithm assumed the material on the central axis to be laterally infinite, thus they fail to account for the portion of the subspot that may be traveling through the material of different densities. This is another example. The bone and the lung equivalent slab were placed next to each other in a phantom such that the interface approximately coincides with the central axis of the beam. A 2 cm thick target was assumed underneath the bone-lung slab. The dose was calculated using both the pencil beam algorithm and the Monte Carlo algorithm. The lateral dose profile was measured using gaphrochromic EBT3 film placed immediately behind the bone-lung slab. Figure B showed that the PBA failed to account for the inhomogeneity caused by the bone-lung interface. The PBA algorithm overestimated the dose at the interface on the bone side and underestimated the dose on the lung side. The lateral dose profile predicted by the Monte Carlo algorithm matched the measurement on both lung and bone side. As previously explained, the PBA has limitations. The question that arises is what is the impact of these limitations? A comparative analysis between a Monte Carlo algorithm and the pencil beam algorithm was conducted for a total of 50 patients with 10 patients per side, including the liver, pelvis, brain, head and neck, and the lung. The difference was evaluated using 4 dosimetry indexes based on the dose volume, a 3D gamma index analysis, and estimated the tumor control probability. Among the liver, pelvis, brain, head and neck, and the lung, the difference between the analytical algorithm and the Monte Carlo-based algorithm was largest in the lung, in which the D95 predicted by the Pennsylvania algorithm was 6.5% lower. The TCP difference can be larger for the lung and the head and neck, but smaller for the brain, pelvis, liver. Therefore, institutions should work to implement Monte Carlo-based algorithm for thoracic and the head and neck application for proton therapy. Another crucial aspect of those calculations in particle therapy is related to the relative biological effectiveness. Treatment planning is based on specific prescription dose to the target and the constraints for normal tissues, and it is not on clinical endpoints such as TCP and NTCP. Given that we currently use dosimetric indexes when treating patients with different modalities, we have to consider the potential difference in biological effectiveness. Therefore, to benefit from the extensive experience of photon treatment, proton therapy prescriptions are based on the physical dose multiplied by a factor to account for the difference in biological effectiveness, which is an RBE, at the same dose when treating with photons. Currently, a generic RBE, namely 1.1, is used as the proton beam RBE. However, the proton beam has a higher RBE value at the distal end of the SOBP owing to the increased linear energy transfer of the protons. Therefore, there is a risk of overdose to the normal tissues located at the distal end of SOBP associated with a higher RBE. In proton treatment, the risk of necrosis and brainstem injury is a concern when treating brain tumors with proton beams. As shown in the graph on the right, the biological dose in the brainstem is potentially higher than that computed using a generic RBE. The original reason for the adoption of a generic RBE was as follows. The mean arity at the center of the SOBP made with the broad proton beam was similar to or slightly higher than that of 250 kV X-rays. Therefore, the RBE relative to cobalt-60 was expected to be similar to that of 250 kV X-rays. The RBE measured in vitro for 250 kV X-rays was approximately 1.15. Only a modest variation of RBE with depth in the SOBP was expected owing to the small change in arity, except for the terminal few millimeters. Given that the strategy employed for higher dose than those of proton therapy, any error in the selected RBE should result in an RBE on the low side to avoid underdose of the tumor. Therefore, a generic RBE 1.0 or 1.1 was adopted by proton therapy centers. Then, how can we use variable RBE, which changes along the depth of SOBP? 8 RBE prediction models varying with depth in the SOBP were validated against experimental data for clonogenic cell survival of V79 hamster cells. As shown in the comparison graph, the Weidenberg model is considered to have the best accuracy. However, the large error range of experimental data limited the determination of the model accuracy. Unfortunately, RBE of particle therapy has not been well quantified, and it is dependent on many factors, for example, arity, clinical endpoint, tissue type, fractionation scheme, patient-specific radiosensitivity, physical dose. The graph on the right shows the RBE as a function of the LET for a 2-gray proton dose, whereas the graph on the left shows the RBE for a 6-gray proton dose. The mean RV over the 6th grade dose is lower for the same RT. Therefore, the RV values in tissue are not known accurately. Nonetheless, the RT can be accurately calculated from the treatment plan information. The RT does not uniquely determine the actual proton RVE. It is an indicator of a local increase or decrease in RVE. All in all, a consensus has been reached. Proton RVE increases as an approximately linear fashion with the LT. Hence, rather than the RVE optimization, LT-based plan evaluation and optimization for proton therapy is thought to be a solution. Reducing RVE-associated risk is especially important in cancer treatment of disease sites such as head and neck, where there are many critical organs such as brainstem and optic nerve structure in the proximity. The figure in the slide exhibits that the different RT distribution can be obtained from the beam optimization for equivalent dose coverage of the tumor. Therefore, various LT or RV-guided plan optimization approaches have been proposed. In the early stage of LT-guided optimization development, two-step IM50 optimization method were proposed to achieve a superior LT distribution. In the first step, dose distribution was optimized to meet those requirements, and the LT distribution was modified in the following step. This two-step method was able to achieve superior LT distributions while maintaining equivalent dose distributions. Instead of a two-step optimization, recent studies aim to optimize dose and LT distribution in the inverse planning for proton therapy. LT distribution was integrated into an IMPT optimizer using various cost functions, which takes into account the LT and the dose distributions. This one-step optimization could search in a larger solution space than the two-step optimization method and possibly can lead to a better quality IMPT plans. The LT-based optimization function will be available in a commercial TPS. A proton track and the objective in IMPT optimization was developed by research, and the plan qualities were tested for intracranial patient cases and head and neck patient cases. Difference in biological dose between the Weidenberg RV model and the RV model of 1.1 for the dose and LT optimization plan were compared. As shown in the figure, the LT optimization plan reduced the mean LT in the critical structures and actually increased the mean LT in clinical. Now, I'd like to move on to one of the interesting treatment proton technology, proton arc therapy. Spot scanning proton arc therapy is an emerging technique that is able to deliver the proton beam through a dynamic rotational gantry. For many plane comparison studies, some preliminary results demonstrate the potential clinical benefits for various disease sites, including prostate, head and neck, lung, and brain cancers. For example, proton arc could significantly reduce the dose delivered to the hippocampus and the cochlea in patients being treated with whole brain radiation therapy. Regarding the efficiency of the delivery of the proton arc plan, the MU and the beam delivery time of PAT were compared with conventional pencil beam scanning for whole brain cases. As shown in the graph, proton arc therapy plans could potentially achieve similar or faster delivery time in modern proton machine with energy layer switching time of less than 1 second. In addition, the right-hand side figure shows that the PAT plane does not use energy layer less than 125 MeV. This demonstrated that PAT could effectively reduce the total MU from the lower energies. Therefore, proton therapy delivery could be more efficient than the conventional IMPT in some disease sites as the beam on time for lower energy is longer. Lastly, I'd like to present the proton flash therapy as an emerging technology of proton beam radiation therapy. Flash radiotherapy is the delivery of ultra-high dose radiation, several orders of magnitude higher than what is currently used in conventional clinical radiotherapy, and it has the potential to revolutionize the future of cancer treatment. Flash radiotherapy induces a phenomenon known as the flash effect, whereby the ultra-high dose radiation reduces the normal tissue toxicity commonly associated with conventional radiotherapy while still maintaining local tumor control. The underlying mechanisms responsible for the flash effect are yet to be fully elucidated. The flash effect has been confirmed in many studies in recent years, both in vitro and in vivo. Even the first patient with T-cell cutaneous lymphoma was treated using flash radiotherapy. The right side of the graph shows the typical TCP and the NTCP plot for conventional dose rate. When flash beam is irradiated, the TCP will not be changed, but NTCP will shift to the right due to the increased resistance of the normal tissues to the ultra-high dose rate beam. Therefore, flash effect has a threshold and dependent to dose and dose rate. Here, flash effect is quantified by defining the dose modifying factor, which is the ratio of the flash dose to the conventional dose rate dose, both resulting in the same assay and endpoint. Therefore, the ratio of the isoeffective dose for conventional dose rate and ultra-high dose rate. To achieve the required flash dose rate, the beam currents from the accelerator need to be very high, but the current accelerator for proton therapy can achieve the flash dose rate only with 230 MeV protons. Therefore, all preclinical studies have been performed in the transmission field rather than using broad peak of 230 MeV proton beams. Clinical trials for human patients are undergoing using the transmission flash beams. There are so many issues related to the flash proton beam treatment, but this is the very short summary of the flash proton beam treatment. Shoot-through or transmission beam is applicable for diverse disease sites. Results are being conducted on dose rate computation and maximally allowed OAR flash volume. In-house developed or commercial treatment planning systems are under development. RB for proton flash is an important issue, and the long-term toxicity of the flash beam needs to be carefully investigated. The outlook of the proton therapy from the physics perspective is as follows. The proton therapy system is anticipated to be smaller and compact, and thus proton therapy hoped to be more cost-effective. Pencil beam scanning will resolve the motion-related issues by developing faster beam delivering system. Proton arc therapy potentially can be a major pencil beam scanning technique, as like the VMAT in X-ray therapy. In the long term, the proton therapy potentially evolves into flash beam proton beam therapy, but it will take many years. Lastly, I'd like to thank Dr. Dong-ho Shin for providing many slides for this talk. Thank you.
Hello. Thank you. Thank you, Professor Han, for a very detailed and nice presentation on proton beam therapy. It was a very nice presentation, very detailed, starting from uh, basics to the clinical part and flash therapy. Thank you very much, Professor Han. Any questions, comment, please, from audience? Participants, please, any questions, comments? I am not seeing any comment in the chat box. So I think there is no questions. Hello? Hello? Hello, Professor Han?
Yes, I can hear you. I'm sorry.
Yeah. Yes. Thank you very much for your nice presentation. And I think there are no questions. It was already late. So I will give you a little introduction right now. Professor Youngyih Han, she is a PhD and professor and chief medical physicist in the Samsung Medical Center. She is in the Sun Kian Kun University, and she has a very vast experience in the medical physics. She is a member of many societies. She is examiner in the Korean board. She has around 16 patents with her name. So she has a lot of experience in the medical physics field. Thank you very much, Professor Han. I have a little question I wanted to ask.
Yes,
I wanted
please.
to ask one thing because the conventional photon beam therapy was there, and it is there in most of the cases, most of the centers. How the dose is equated for proton beam therapy, like in head and neck, how the total dose is decided. Like in, for example, in head and neck cancer, we deliver conventionally 70 gray in 35 fractions with photon beam. So how with RV, how the dose is decided, how much dose to be delivered, like in nasopharynx or somewhere?
Actually, our center used the generic RB 1.1. So
Yes.
The doctor just calculated the biological dose equivalent to the photon dose. However,
Yes.
Doctors always try to find the better way, rather than the value of RB, better way to increase the fractionation. So there are several clinical trials are undergone to find the difference between the proton delivery protocol and X-ray delivery protocols. But actually, in our center, we don't use any valuable RBs.
Okay. Okay. Just whatever there in literature you are delivering, deciding the dose.
But
With that.
yes, but one of the observation during the last 5 or 6 years, doctors observed a little bit of a different toxicity pattern treated with the protons. That could be attributed to the different RBE for each organ for proton beams, but it's not possible to quantify the difference. So we are waiting for the release of LT-based optimization, not the RB-based optimization, because it's not clearly known that what is the real RB for in each organs.
Okay, thank you, Professor Han. Now I will give mic to Professor Arun Chogle, sir. Is he there? Chogle, sir?
Arvind sir, so regret for that inconvenience. Professor Chogle won't be able to join us. Anyway, I'm there to substitute him for a while. So thank you very much, Professor Han and Professor Shukla, for such an dynamic presentation and webinar. And we regret the inconvenience to both the speakers, moderator, and our participants for today's little bit inconvenience in time of starting the webinar because of some technical issue. But thank you very much at last, Professor Han, for such a wonderful presentation. It was a very important topic, and nowadays it interests most of our youth because proton therapy is something which everyone wants to know about nowadays. And so let me introduce Professor Shukla also a little bit, as he's one of the pioneer medical physicists in India too. And currently he's an associate professor in Udaipur Government Medical College. And he has published extensively in brachytherapy and radiation dosimetry in protection. So thank you, Professor Shukla, for such a great moderation. Professor Han for such a good presentation. And of course, to our participants to bear that inconvenience and be with us. And I would like to inform you regarding two of our upcoming programs. So can you see my screen?
Yes. Yes, we can see.
Yeah. Okay. So our next webinar will be on 3rd of November. That will be on biological targeted radiotherapy, utilizing imaging biomarkers for precision radiotherapy and treatment response by Professor N.T. Hotway. And I also want to welcome you all to AOCMP 2022 that will be in Taipei, Taiwan. And the clock is ticking and we are very near to the program. So I welcome you all and encourage you all to please join us in Taipei. This conference will be organized in both the modes. I mean to say in hybrid mode and in hybrid mode. It means you can join online also, and you can physically also join the conference. So thank you very much, all of you, for being with us. Thank you, Professor Han, Professor Shukla, at last. And I welcome you all to our next webinar and to Taipei also. Thank you so much.
Thank you.
All right. Thank you.
Thank you.